Yeah, thank you very much for the kind introduction and for the invitation and for the organizers for organizing this beautiful conference. So today I will talk about Markov chain curvature and mixing. So first a bit clarification of the terms. What are Markov chains? So probably you all know. So you can think of random walks. Then they have many applications in network science and graph theory. And they are also very useful for interacting particle systems. So we will talk a bit about interacting particle systems, how to apply curvature to some of them. Then just very general, what is curvature? It denotes the deviation from flatness, and it's a very useful concept in general. Like, yeah, basically the whole conference is about curvature. And yeah, a few applications of the discrete curvature is like particular quantum gravity. There have been a few works about it. Then in applied network science, you can do network analysis. Yeah, and has also been used for optimal transport, and the path coupling method is one of the key features I will talk about and how this is used. Then the third part of the talk is the mixing. So there are several ways to measure how quickly Markov chains converge to equilibrium. So for example, you can measure how quickly the entropy decays. So that's related to the Log-Sobolev inequality. And you can also measure how quickly the L2 norm decays. And this is the spectral gap or Poincare inequality. And there are a few other ways, but these will be the main ways of mixing I will talk about, assuming some lower bounds on the Ricci curvature. So here's the overview of the results I want to present. So the first thing is the conjecture by Perez and Tetali about Markov chains with positive Ricci curvature. So their conjecture was that this Log-Sobolev constant can be lower bounded by the lower Ricci curvature bound. Yeah, a bit of a spoiler. In general, this is not true. There's a very easy counterexample I can show you. And if we have an additional assumption, which corresponds to some L infinity Wasserstein decay in the heat semigroup, then we do get this entropy estimate, this Log-Sobolev estimate. And the second part is about Log-Sobolev inequalities and also isoperimetric inequalities, assuming non-negative Ricci curvature. And yeah, what we do there is lower bound the Log-Sobolev inequality by 1 over diameter squared up to some constant depending on the Markov chain, the minimum jump rate. And the third part, if time allows, is the Naur-Millman conjecture. That was the question if non-negatively graphs can be expander graphs. So that was first solved by Justin Salé using Benjamini-Schramm limits, but this was, because of the technique, a purely qualitative result. And today, I would like to talk a little bit about the quantitative version, that one can estimate this relaxation time or 1 over spectral gap by the average distance. That's the overview. Now let's introduce a bit the setting. So the setting is very simple. We are just on a finite state space, have a Markov chain on this, and we assume some laziness for simplicity. We assume irreducibility, and for most of the talk, we don't need reversibility. So many things work for irreversible Markov chains as well. So once you have this Markov kernel, there's a natural way to get the Laplacian from it, which is just that you subtract the identity from it. For some applications, it will be useful to also consider Laplacians which are not bounded by 1. So then you can think of, you just take this Laplacian P minus identity and multiply it by a large constant. Then it's still conceptually a Laplacian, but it cannot be produced by such a P minus identity. But still you can calculate the curvature in the scales as you would like. So now, yes? Yes, Markov kernel, distance d, that's all input data.
Yeah, and you can't hold the
exactly. Right. So yeah, then this Olivier condition introduced by Jan Olivier in 2009 is that the expected distance among some coupling is just decreasing with rate 1 minus k. So actually, it was not really new by him. So it was known already in the 70s, this condition, but not identified as Ritchie curvature. So before it was called the Dobrushin criterion or also path coupling method. And there's already been works on this before. So like there's one thing which is kind of a very obvious question when you see this, namely that you have the two input data, the distance and the Markov kernel, and they are like totally independent yet. You can choose the distance no matter what is the Markov kernel and vice versa. And a nice question for the audience, because I'm not really an expert in metric measure spaces, is what happens if you do this on, say, Riemannian manifolds or metric measure spaces? Is there like any research on this? I have seen this in the context of sub-Riemannian manifolds a little bit, that you have like a second gamma operator in the vertical direction and one gamma operator in the horizontal direction, but you always have like some additional assumptions. But to my knowledge, I've never seen like decoupling the distance from the Markov kernel in full generality and try to derive as many results as possible from the typical Riemannian case. So one advantage with this would be that if you have non-constant curvature bounds and you just want to investigate properties of the Laplacian, that you can optimize over the distance to try to get the best possible curvature bound. So typically, you will have some maximum principle that in the optimum, the curvature should be constant, but that's also not very clear. So that's maybe something we can talk about in the break, if you like. Okay, then there is a characterization of this Olivier curvature using couplings and using this Wasserstein decay. So that's well known, for example, from the Renesse-Sturm paper in the manifold case, and many characterizations hold true in the discrete case as well. So the lower Ritchie bound is equivalent to discrete time Lipschitz decay. That's the second bullet point. It's equivalent to continuous time Lipschitz decay. That's the third time, with e to the TL being the heat semigroup. And this is also equivalent to Wasserstein contraction. Then there is a nice formula, which is useful for the talk at some point. Radoslav Wojciechowski and myself, we discovered in 2019. So that is that we can also express the Ritchie curvature purely in terms of the Laplacian instead of using the Markov kernel. So one nice feature about this is that if you consider infinite graphs, you are able to handle graphs with unbounded Laplacian. Well, when you have a Markov chain, discrete time, you cannot do unbounded operators. And then you can investigate properties like stochastic completeness and many other things. But today we restrict to the finite case, just to keep this formula in mind. Now there are a few well-known consequences of non-negative and positive Ritchie curvature. So the first is that we get a spectral gap or Poincaré estimate, and the second is that we get a diameter estimate. So this looks a bit different than in the Riemannian case, right? It rather looks like an L1 thing. In the Riemannian case, we have the square root of the dimension divided by k, and here it's without the square root, and the reason, the conceptual reason, is that the distance is an L1 distance, if you think of a grid, and in the Riemannian case, it's like an L2 distance, so this explains the discrepancy between the exponents. So then there's also an important result, which is the so-called concentration of measure phenomenon. So now we assume we have the hop count distance and reversibility, and we have some Lipschitz function which is centered, then most of the mass is concentrated around the average of the Lipschitz function. These are the well-known consequences from Olivier. Then also in one of his papers, he introduces some notion of sectional curvature, which I'm not very sure if this really corresponds to the Riemannian sectional curvature. So what is this? Well, actually, we can only really distinguish between non-negative and negative sectional curvature. And this means that we can find a coupling of the random walks such that the distance decreases almost surely. So that is in contrast with the Ricci curvature, where you only need average distance to decrease. And for some technical reason, we will impose this on the adjoint operator with respect to the L2 space and not on P itself. So now there is a characterization, or at least some implication, of non-negative sectional curvature. So first, I discovered this with my co-authors Mark Kempton and Gabor Lippner, and we didn't call it sectional curvature. We had a different combinatorial characterization, which turned out to be equivalent, and that is that we have the log-Lipschitz decay under the heat semigroup. Yeah. Turns out that you also have another characterization using the L1 Bakri-Emery estimate, but I don't have this on the slides over here. Interestingly, if we have the hop count distance, we get also the converse direction, and there's like a discrepancy to the manifolds case, namely that in manifolds, this Lipschitz decay also characterized non-negative Ricci curvature, and the problem why this isn't true in the discrete case is the lack of the chain rule for the Laplacian, for the gradient, which is like a leading problem in the discrete setting that many calculations you want to do, you would like to have a chain rule, but it's just not true in the discrete case, and for describing curvature, the approximations are not good enough. Okay, so the idea of the proof of this log-Lipschitz decay is, okay, we assume we have some coupling of the Markov chain, and then the first inequality you see is just by the definition of the Lipschitz constant. So you want to estimate the log of Fy star. And the second inequality you see in the middle is the consequence of the non-negative sectional curvature. So you estimate the dx star y star by dxy. Then having this inequality, you can take exponential expectation and logarithm again, and then you are more or less there. So the computation is quite simple, but still it will have some nice consequences related to this Paris-Theta-Lie conjecture. So first, let's do some examples with the non-negative sectional curvature. So the birth-death chains are, like always, the easiest examples, and there you can characterize the non-negative sectional curvature by monotonicity of the Markov jump rate in the both directions. So in the one direction, it must be increasing, in the other direction, it must be decreasing, and if you have this, then you have non-negative sectional curvature. So there are also some more nice properties. So it's compatible with taking Cartesian products, which means it's probably a useful property to investigate infinite dimensional systems, or at least high dimensional systems. And there are many interacting particle systems where you also get non-negative sectional curvature when using the right distance. Right? You remember, we can still choose after knowing the Markov chain what the distance should be. Now, one explicit example where we have the non-negative sectional curvature is the zero range process. So this is an interacting particle system on some geometry, and the jump rates where a particle jumps to just depends on the number of particles at the state. It's not interacting with the number of particles at other states. So what we have to do here is we have to take the not the hop count distance, but the L1 distance, or called Hamming distance. So this only coincides with the hop count distance if this underlying geometry matrix Gij is like a complete graph or supported everywhere, which is typically not the case. So to say, choosing this distance gives better properties for the non-negative sectional curvature. Okay, now the proof idea for this zero range process having non-negative sectional curvature goes like this. You take some state with m particles, and you take two of them, which have distance 1 to each other. So this means you will find a state with m-1 particles, which we call z, and then we construct the zero range process by first moving z, and then the remaining particle can be considered as a conditional process on z, and for xt we call it this remaining particle IT, and for YT, we call it JT. And for all times, the two processes will just differ by one particle, which means that the Hamming distance will always stay 1, which means that we have non-negative sectional curvature. Okay, so for the zero range process, we can also calculate the Ritchie curvature. And here we have these rates Ri, which tell you how high is the jump rate if you have at one side k particles at side I. And the Ritchie curvature is lower bounded by the minimum of these jump rate differences. So one thing to recall, if this Ri is just linear, then it corresponds to the independent process. So the proof idea is as before. We do the same coupling, and we just consider the minimum jump rate for this IT and JT. One more assumption is that we are in the mean field case now, right? You see this Gij is constant independent of the I. So, and as we are in the mean field case, we always have some probability of IT and JT that we can jump to the same side. We can couple them in such a way. So all we have to do is find the minimum jump rate of the IT and the JT, and that is precisely this minimum of these jump rate differences. And from this, we get the Ritchie curvature lower bound. Okay, now let's talk a bit about entropy contraction and Lox-Sobolev inequality. So the entropy is defined in the usual way. So pi is the irreducible measure, and we have the relative entropy with this. Then we have two versions of entropy contraction. The first is the discrete time, where we just consider how much the entropy decays of one step of p, and the continuous time, where we look at the entropy contraction along the continuous time heat flow. So for the continuous time heat flow, this contraction rate is called modified Lox-Sobolev constant, and we will give estimates for this. So now let's come back to this Perez-Tetali conjecture. So he conjectured if we have just a lower Ritchie bound on the Olivier-Ritchie curvature, that we can get a lower bound on the modified Lox-Sobolev constant in terms of a global constant times the curvature. Now, there were many attacks trying to prove this conjecture, and it turns out that in this generality it's wrong. And the counterexample is very easy. You just have 3 states. I'm going to draw it here. And what you do is you have some jump rate in this direction, and you make this jump rate over here very small and keep all other jump rates fixed. Then it turns out that if you choose the right jump rates for the other edges, then you can ensure that you have uniformly positive Olivier curvature. But as this one jump rate goes to 0, then this modified Lox-Sobolev constant will go to 0. So this means there's no chance to find such a universal constant C. So in the end, it means we just need some more condition, and that is precisely the non-negative Olivier sectional curvature. So that's the theorem we have. If we have non-negative Olivier sectional curvature, then the Lox-Sobolev constant and even this entropy contraction rate is lower bounded by the minimum Ritchie curvature. And the proof idea is also not so hard. So we assume we have some measure mu, which attains this entropy contraction rate. And then we use variational principle to characterize this, and we just look at the Lipschitz constant of this. Maybe a few words where things come from. So here we get rid of the P star F. This is the non-negative sectional curvature, and the inequality over here is just the Lipschitz decay of P. this is Ritchie at least K. This is non-negative sectional curvature. Okay, now let's apply this again to our mean field zero range process. Well, we just combine the Ritchie curvature, sectional curvature, and our log-Sobolev estimate, and get that the log-Sobolev constant is at least this minimum difference of the jump rates. So one remark is that this seems to improve all previous bounds in the sense that the previous bounds were kind of bad when this maximum difference was large, right? They kind of needed some gradient estimate to keep this maximum difference small to get the conclusion of the large log-Sobolev constant. So here we get rid of this and have a very clean result. Okay. Now we will come to the next part. So as you might have noticed, we have this modified log-Sobolev inequality. There's also the standard log-Sobolev inequality. And it turns out that they are different in the discrete setting, again, by the lack of the chain rule. Although on manifolds, they are just the same up to a factor. So the difference between them is the way we define the energy. For the modified log-Sobolev, it's the energy of F together with log F. And for the standard one, it's the energy of square root F. And there is a general inequality that the non-modified is the smallest. Then we have the modified, and this is smaller equal the spectral gap. So the next step, as I told, is case we have non-negative Ritchie curvature, and we want to give a lower bound of the unmodified log-Sobolev constant. So here we need some way to control the scaling. So maybe one would like to use a dimension term, but because you are in principle allowed to scale the Markov chain up by a factor, we need this something like the P0 over here. And the P0, you can think of the minimum jump rate, but it's weighted with a square distance. So yeah, we don't allow 0 jump rates, but all the positive jump rates. And the assumption we need for this theorem is that we have some kind of path distance being compatible with the Markov chain structure. Which path distance does not matter. Okay, so let me first ask you another question if you have seen something like this in the Riemannian setting or in any kind of setting. So that is a characterization of the log-Sobolev constant just in terms of Dirichlet eigenvalues. So what you do is you think you have your space, then you separate it into pieces, into W and to W complement, and you consider the Dirichlet eigenvalues on both of the pieces. And what you do then is to take the logarithmic of mean of these two. Yes, that's what I do. Wait, what was that? Did I give the definition like this? So here's the definition, it's the best one. Yeah. Yeah. Yeah, just thinking of the best one. So basically this best log-Sobolev constant can be estimated as some mean of these Dirichlet eigenvalues of this part, and you infimize over the partition. And yeah, what you have to take in this case is the logarithmic mean. So some intuition is, well, if you take the arithmetic mean instead, you basically get up to a constant, the Poincaré constant, or the spectral gap. So if you have seen anything like this, I would be very glad to hear about it, like in any setting. So in my case, I've proven this for graphs only, but I very strongly assume that it should be just the same in any setting. So that will be a tool for proving this non-negative curvature estimate. And the proof idea is that one can use an isocapacitary characterization of the log-Sobolev constant. So the capacity is if you fix A and B, and you only do the infimization over the function f, and then you take the energy of f. So that's considered the capacity of f. So yeah, and draw another picture. We think we have like a partition into 3 pieces. The one has to be like large. Then we have some small piece, call it b. Then the function is f is constant here, and here we are harmonic. And consider the energy of this, and then divide it by the measure of the smaller set. And we also have this logarithm term, which basically makes it log Sobolev. If you skip this logarithm term, you just get the spectral gap again. Yeah. Then once you have this, you can apply this to the setting above and get like very bad constants, because this isoperimetric characterizations comes with bad constant, but still you have universal constants. This expression here looks 0. No, well, you want B to be non-empty. I mean, if B is empty, the denominator is 0 and the thing blows up, so it's just not the right thing. Okay, no worries. Okay, now in order to get there, there's actually a conceptually stronger result, namely we get some isoperimetric inequality. So we define the boundary measure kind of the usual way, but we have to also take into account the distance. So when you usually maybe see the boundary measure of a graph, you just have that you count the edges going between the 2 sets. But here we also have to take the distance between the 2 points into account. Then there is this observable diameter, where I'm a bit sloppy, like typically people call this separation distance, but conceptually they are just the same and differ only by a constant. So that's, yeah, we can think of the same picture. We have 2 sets, A and B, with small measure, and we consider the distance between them. So this observable diameter is the inverse of the concentration profile. So therefore we get, in the end, an estimate between isoperimetric profile and concentration profile. So for some technical reasons, we have to take this closure, but this is not important conceptually. So what's the theorem we have now? So again, like always, we assume non-negative Ricci curvature, and we fix some set W and some epsilon between the measure of W and a fixed constant. And then we can estimate the isoperimetric profile here, that's the isoperimetric profile, by the concentration profile on the right. And the nice thing about this is that we don't need to know any information about the tail of the concentration profile. It's just, we already get the good estimate, assuming 1 point from the concentration profile. So you can choose every point from the concentration profile, and we'll get a good estimate for every point of the isoperimetric profile. So in a sense, this can be seen as a discrete analog of a result of Emanuel Millman, where he gave similar estimates. I think in his version it was not really clear that you can do it pointwise. So like it appeared to depend on the tail, but it's not really true that it depends on the tail. Okay. Now let's give a few proof ideas. Time, like 15 minutes, right? Yeah. So the proof idea is based on a mean curvature argument. It turns out that in the end, we cannot fully implement it in a discrete setting, but that's where the idea comes from. So if we assume we have some set minimizing the boundary given the volume, then the boundary should have constant mean curvature. And yeah, how we can understand mean curvature in the graph setting, that is exactly as the Laplacian of the distance from the set. Then we can use the volume comparison using the mean curvature. That is that the boundary measure away from the set grows at most exponentially with rate of the mean curvature. Yeah, under the assumption of non-negative Ricci curvature. So then there's also the Laplacian comparison. So that is that the Laplacian decreases going away from the set if you have non-negative Ricci curvature. And what you want to do in the end, you want to improve this Laplacian estimate. So so to say this H might be positive, but in the end, you really want to have a negative constant. You want to estimate L of some function to be negative. And what you do is you replace the distance of W by some function depending on the distance of W, which is concave. So you still get the same estimate in the first part, but for the second part, you will get some additional negative contribution if you have a concave function, and you will adjust it in such a way that you can use up the whole gradient. So you can. Here we think we have diameter, and the function will just look like this, and he will hit slope 0. So that is how you should think of a function phi we will plug in over here. And now once we have this estimate of the Laplacian with a negative constant, then we can directly get the isoperimetric estimate the boundary against the volume of the set, and we also immediately get an estimate on the Dirichlet eigenvalue. So that is the second. So in the end, this first estimate will give you the isoperimetric theorem I gave you, and from the second estimate with the Dirichlet eigenvalue, you can derive the Log-Sobolev inequality from the characterization with the Dirichlet eigenvalues. Okay, now that was the idea from manifolds, how to implement this in a purely discrete setting. So you remember, we don't have a chain rule, we have to have some excuses, and we don't have a concept of mean curvature. And there's maybe not a way to do this, but one can kind of get around this. So we think we have a tripartition of our set again. So the picture again looks like this, except we can we rename this V, we rename this W, and this in the middle, we rename K, and we think of K being very slim, and K plays the role of the boundary. Now, what we are looking for is something with constant mean curvature. So basically, we want some function with constant Laplacian on set K. That's the first assumption. Then, well, we want this F to mimic the distance from K. So we want that it behaves like the distance on V and on W. And we mimic this by requiring that the maximal Lipschitz extension of the function on K on the set V and the minimal 1 Lipschitz extension on W. Then once you have these properties, the last two properties will follow automatically from non-negative Ricci curvature. So the Laplace estimates on V and W. So one severe drawback is if you want to mimic mean curvature, you would love that the function is roughly constant on K. But I don't see any chance to make this happen. I was trying for 2 years, but didn't work. So at the end, I was just accepting we don't get it. But the nice thing is, even if you don't have that the F is roughly constant on K, you can still proceed to, like in the manifold case, and use your chain rule to get finally the isoperimetric and the Log-Sobolev constant. So now, assume we have found this nice function F, then we don't have a precise chain rule, but we have a good enough estimate for the chain rule. So, if you remember in Riemannian case, we had like an equality over here. Yeah, So here is, so to say, the gradient of f missing, but we are, the gradient is 1 because we are the maximal Lipschitz extension, and we get that factor P0 from, so to say, Taylor expansion. So P0 was this minimum jump rate. And this chain rule estimate will self-improve the estimates of LF on V and LF on W. So we will get negative constants, some sense on both sides, which is good enough to get the isoperimetric and the log-Sobolev inequality. Okay, let's talk about a few corollaries. The first is if we want to get back the Cheeger inequality. So Cheeger inequality is just boundary measure divided by volume measure, and you minimize over all subsets. Then we can sandwich the Cheeger inequality using the concentration profile and just using a single point of the concentration profile. So yeah, there is still this discrepancy with the P0, which is like something quite typically happening on graphs. So for example, you have the Cheeger-Boozer inequality, and also you get this P0 as like a factor in between the two sides. So this first inequality is a very general estimate. You don't need anything. So, but the second is a consequence of the corollary of the isoperimetric inequality. Okay, then we can also get back the Gaussian isoperimetry from the Gaussian concentration profile. So that is, we assume we have Gaussian concentration, which I told you in the beginning is also a consequence of positive Ricci curvature, but now we just assume it, and we additionally assume non-negative Ricci curvature. Then we can get a bound on the log-Sobolev constant. So here, unfortunately, we have this P0 squared, and yeah. So in the first step, we don't get the log-Sobolev constant, but the Gaussian isoperimetric constant, but they are, so to say, also in one-to-one relation, just up to this factor P0. So there was a question by Erba and Fatih, which they originally asked in the case of entropic curvature, which is the curvature Eva talked about yesterday. And yeah, they were asking if they can get some connection between the log-Sobolev constant and Gaussian concentration in this direction, and also the previous question they asked, and it was and is still unclear for the entropic curvature, but here you see some presentation how one can do it for the Olivier curvature. Okay, now let's apply it again to zero range processes. So now we take zero range process with all rates constant. So before the rates were increasing, now they are constant, so we don't have positive curvature anymore. Turns out that here we don't have non-negative sectional curvature anymore, but for the theorem here, we didn't need this. And having all this, we get the estimate for log-Sobolev constant with the diameter square from the theorem. And this improves some result by Erba and Fatih by factor of log n. Now, I think I still have 5 minutes for the final part. So, yeah, what we want to do is show this expander graph question. So the question was, do you have expander graphs with non-negative curvature? And we wanted to give a quantitative bound on the spectral gap. So the starting point is the Lipschitz contraction in terms of the infinity norm, which is just well known in case of metric measure spaces, and also not much more complicated in the discrete setting. So let's skip the proof. Yeah, so these are also some kind of well-known consequences of non-negative Ricci curvature. So like kind of a worse version of what I told you is that the spectral gap is bounded by 1 over diameter squared. So the theorem I presented is an improvement of this. And yeah, so here's the recall of the question. So expander graph is a sequence of graphs which have bounded degree, but the spectral gap is uniformly bounded away from 0. So one more remark is that if you could prove polynomial volume growth of the graph, you would get it immediately, but the polynomial volume growth of non-negatively curved graphs is still a very open question, at least in the Olivier curvature setting. You have to make some additional assumptions like uniform weights, otherwise you can take biased birth-death chain and don't have a chance, but still I expect very strongly that in some nice setting where you have just a combinatorial graph, you should have polynomial volume growth in case of non-negative curvature. Okay, so as I told you, Justin Salé was proving this theorem using the Benjamini-Schramm limit, but there was no quantitative version yet. So how does the quantitative version work? So here we introduce some average mixing time. So that's the time it takes until the integrated heat kernel integrated over both directions is close to equilibrium in L1 norm. That's basically already the main theorem, that we find an upper bound on this mixing time in terms of the Giga constant. So you can think you can rearrange, put the Giga constant to the left-hand side, and then to this mixing time, this will grow. This average mixing time will grow to infinity as the graphs will grow. There's also one more, a bit more explicit estimate. So now the proof idea is again very simple. So what you do is you consider this sum on the sum on the first display, and you make it a double sum by also summing it over Z. Then if you consider just the first summation, then you see the Giga constant popping up from the co-area formula. And if you do just the second summation, then you can plug in the gradient estimate. So you have this ptx dot minus pty dot and total variation distance. And by the curvature, this will decay in time like 1 over square root t. Yeah, so these two coincide. So you can combine them and get the estimate for the Giga constant. Okay, so this we can finally use for giving like an even more clear estimation of the Giga constant, an even clearer upper bound in terms of the diameter. Well, not the diameter, but the average distance. Yeah. This is just the average distance, and the Giga constant is at most 1 over square root of the average distance, which clearly goes to 0 once the graph increases. One last consequence of this is that in case of non-negative Ritchie curvature, we have precise control between this average mixing time and the spectral gap and the Giga constant. So they coincide up to factor only depending on P0. So that's just the consequence of the theorem, and some of the directions hold true for general graphs. Here's the list of references, and with this, I think I'm at the end of the talk and want to thank you very much for the attention.